A single backend service can register thousands of routes. Every time a request comes in, how does the server find the matching route among all of them within milliseconds? The answer? Almost every high-performance web framework's router is built on a Radix tree under the hood. If you store a single root product in a plain trie, every character gets its own node. One root means 8 pointer hops and 8 allocated nodes. With more roots, both memory and lookup depth balloon quickly. The Radix tree's key idea is simple. Whenever a node has exactly one child, merge it with that child. The whole chain is single branch end to end, so it all merges into one edge that stores the entire string product directly. Now register 3 real roots: product, id, and profile. Product and profile share the first 4 characters, pro, so they share one edge until they diverge at duct and file. Product hangs off the product node. Id is a dynamic parameter branch, whose value is only captured while matching a request. The request get product 42 arrives. The router starts at the root and compares characters segment by segment. First, it matches the shared prefix pro. One comparison skips 4 characters. The remaining path is duct 42. Comparing against the file branch instantly picks the right one. Then duct matches, landing on the product node. What is left, 42, has no matching static branch, so it falls to the wildcard branch id. Capturing id equals 42. The match succeeds. The whole match took just 3 comparisons, completely independent of whether the tree holds 3 roots or 30,000. It only depends on the length of the request path itself. With a linear root list, the worst case tries to match every single rule one by one. The more roots registered, the slower matching gets. A plain hash map can do 1 lookups, but it can't handle dynamic segments like id that are only known at request time. A Radix tree naturally supports both static paths and wildcard branches at its branch points. Now register 1 more root, prod, with no trailing oct. After matching pro, the rest of prod is just d, but the existing edge is the full duct. They diverge partway through, so the edge can't be reused as is. The Radix tree splits the edge. A new intermediate node D is inserted where prod now terminates. The remaining oct becomes its child edge, still pointing to the original product and product. The id branch under product needs no change at all. It just sits 1 level deeper. That is the real cost of inserting into a Radix tree, occasionally splitting an edge, in exchange for a tree that always stays compact. Gin and Echo and Go, Actix Web and Rust, and Fiber and Go all use a Radix tree or a close variant at the core of their router. They share the same pattern. Roots are usually registered once at startup, then matched over and over by every request, a perfect fit for this write rarely, read constantly workload. At its core, a Radix tree compresses character-by-character comparison into segment-by-segment comparison. Lookup time depends only on the path length, not the total number of roots, and it naturally supports wildcard and parameter branches. That is why nearly every performance-minded web framework reaches for it as the core data structure behind root matching.